All right, so in this video, we're going to talk about different types of reactors, and we're going to try and keep it really short so that you can understand the main principles before we get to class. All right, so first things first, what is a reactor? Right, a reactor is basically just a type of system. We have some kind of a boundary. Many times it's a container that we're dealing with as a reactor. There's some flow rate that's coming into the reactor. There's some volume associated with the reactor, and there's some flow rate leaving the reactor, right? So you'll see in this particular diagram that's on the screen, you're going to have different concentrations. You could potentially have mixing going on within your reactor, and you have a system boundary and you have a vessel and a container. So reactors are basically a type of chamber that we use to give us system boundaries in order to solve engineering problems. So, a couple things really important. We've talked about this before with kinetics. Temperature is key to reactor design. So temperature it governs the rate of reaction, right? So it can be negligible if we're in what we call a very dilute solution. So temperature won't affect the solution itself. But what we will normally care about when we talk about reactors is how the temperature affects the reactor's surroundings. So we have two different types of reactions that we talk about when we talk about the temperature. We talk about an exothermic reaction, which is when heat is released, and we talk about an endothermic reaction when heat is absorbed. And so just the key point here is to remember that, again, temperature influences your rate of reaction, and that's important. So I'm not going to go through this slide in detail. What I want you to do is I want you to pause the video and just make sure that you understand these terms. We don't quiz on vocab in this class, but I do want you to be aware of these terms. You'll probably have seen them in a chemistry class in the past. Just pause the video, take a look at the slide, make sure you understand these terms before moving forward. The big thing that I want to talk about in this pre-lecture is three different types of potential reactors that you will see. So these are three different figures that you should know and understand, hopefully by the end of this pre-lecture. So before we talk about those three different types of reactors, we want to talk about reactor operating schemes. So we have two main schemes under which we can operate our reactors. We can use either batch reactors or we can use what we call continuous flow reactors. So continuous flow reactors can have many flavors. We can see plug flow, we can see plug flow with dispersion, and we can see what we call either a continuously stirred tank reactor, a CSTR, or sometimes this is also referred to as a continuously mixed reactor, a CMR. They're the same thing. So two different operating schemes. We can batch in our reactor or we can use continuous flow. So one of the reactors that you need to know is what we call a batch reactor. So key things about this type of reactor. The operation of a batch reactor is very different from a continuous flow reactor. Reactants are charged to the reactor, so they mean they come in. The contents are well mixed and they're left to react. So you can think of it simply as pouring water into a water bottle, adding some chemicals, maybe you add some flavoring to your water. You mix it up and then you let it react so that you have a drink that you like that isn't just water, right? It's got some taste to it. And then the resulting mixture is removed or discharged from the system. So you put the water in, you put your drink mix in, you mix it up, you drink it, and that's discharging it from the system. That's a batch reactor. So in a batch reactor, when we do mass balances, the input and the output terms are going to be zero because we have one input and then we have one output. And so it's not a continuous process over time, right? Remember when we do mass balances, we're talking about over time. We normally talk about flow. So in that case, our mass balance is going to simplify to accumulation equaling a negative reaction consumption. So it's not going to be related to input or output. And then if the batch reactor is first order, the equation that you see on the screen is going to be the way that we take a look at these particular reactors. It looks very similar to what you've seen in the past for kinetics. Another type of reactor that we care about is a plug flow reactor. This is important in water and wastewater treatments because we many times have distribution pipes. We have them for sewers, we have them for drinking water. In steady state, the composition at any point in the reactor is constant with time. So remember from your flow pre-lecture that you have that plug of fluid and it moves through all over throughout that amount of time, and the composition is constant. Remember that this is an ideal case, right? This doesn't always happen in real life. We always have dispersion. We have turbulent flow, we have changes in velocity or changes in direction of the flow. So plug flow, like ideal plug flow, is not really seen in real life all that much. In this case, and when we do a mass balance, our accumulation will equal 0. I apologize, there's no 0 on the slide, but your accumulation does equal 0. So in this case, your input is going to equal your output plus your reaction consumption. And then again, if the reaction is first order, the ratio of the concentration coming out to the concentration coming in is an exponential function related to the rate of reaction. And then remember, theta is what we call a detention or retention time. And we'll talk about that more when we talk about this in class. The last type of reactor that I want you to think about is a CSTR or a CMR reactor. This is the one that we're going to see the most often in water and wastewater treatment. And the key component here is mixing. Mixing is going to create uniformity and provide contact time. I'll say it again because it's important. It provides uniformity and contact time. That's critical. So uniformity basically means that when we have that mixing occurring, as things are being fed and as things are leaving, whatever is being mixed in that center has a uniform concentration. So whatever is coming in quickly gets mixed, and then when it leaves, it's going to have the same concentration that's in the tank, and that's important. So the reactor contents will be uniform over that reactor volume, right? It becomes very important when our reactors get large, and we'll talk about how there's different ways of designing the reactor so that we can have mixing throughout the entire reactor, especially when they get big, right? Wastewater treatment plants are big, they're not small. For the mass balance, unfortunately, there's nothing that we can cancel in terms of terms, so you have to take into account accumulation, input, output, reaction, consumption. And if it's a first order reaction, it looks a little bit different. There's a ratio of concentration leaving to concentration coming in, and that's related to 1 over 1 plus the reaction rate constant, K, times that theta value, which is that retention time. And again, many times that retention time is what we want to find. So I have the equation rearranged here to solve for that retention time, because many times that's what we're looking to solve for. So key things engineers need to know about reactors, right? Batch reactors generally have a lower cost to install because you don't have all the mixing and the rotors and the pumps that you need for a CSTR, but they're higher cost to operate than CSTRs. Normally they're very limited to small installations. They're good for small systems. They're not great when you're treating a huge volume of water. Whenever you're designing a reactor, you need to know how the fluid is flowing. So we talked about different flow regimes in another pre-lecture video. Keep an eye on that because these two things work in tandem. And we need to think about what's the goal of the reactor. If we're providing contact time, we want to use what we call a CSTR. If we maybe want to test in a lab, we want a batch reactor. We just want to test something and be done with it. If we need to maintain fluid movement while providing some treatment, or maybe we need to have a residual in our system, we'll talk about that later, maybe plug flow might be better. So how fluid is moving and the goal of that reactor really does play a role in which reactor you choose. And then the initial and final concentrations, the reaction rates, and the residency times, retention time, same thing, right? All of those parameters are the things that we're going to need to know in order to design these properly. So, significance, because I always like to tell you the why when it comes to these things. Contact time is a key parameter in disinfection. So you need time in a tank to get rid of all the nasty pathogens, right? We talked very briefly in one of our pre-lecture reviews on biology about pathogens, and we disinfect and we get rid of pathogens. So you need to make sure that you have sufficient contact time. That's a key parameter for designing disinfection. So that's one application. Most of your water and wastewater treatment plants are going to operate 24/7, 365. So the fluid needs to constantly be moving to achieve treatment, and you need to be aware of that when you design a reactor. And then finally, the shape, size, and operation of the reactor are going to influence its efficacy. So if we have a specific target final concentration, we need to design a reactor that is going to achieve that. And so that's very critical as well. So here's kind of some key points about why this is going to be significant moving forward.